Quantum theory emerged in the late 19th century, a time when the scientific community was grappling with the limitations of classical physics. The established laws of physics, which had been meticulously developed over centuries, were suddenly found inadequate to explain certain phenomena. This period marked a significant turning point in the history of science. Scientists encountered phenomena that defied classical physics, leading to a sense of confusion and curiosity. They were observing behaviors in nature that simply couldn't be explained by the existing theories. This was a time of great intellectual upheaval and excitement as the quest for new understanding began. One of the most significant challenges was the blackbody radiation problem. This problem involved understanding how blackbody radiation emitted energy dependent on its temperature. Classical physics predicted that an ideal blackbody at thermal equilibrium would emit radiation with infinite energy at ultraviolet frequencies, a result known as the ultraviolet catastrophe. This paradox highlighted the need for a new theoretical framework. In 1900, Max Planck proposed a revolutionary idea to solve this problem. He introduced the quantum hypothesis, suggesting that energy was not emitted or absorbed continuously, but in discrete packets, which he called quanta. This was a radical departure from the classical view and laid the groundwork for a new era in physics. Planck's hypothesis suggested that energy was emitted or absorbed in discrete packets, or quanta. This concept was initially viewed as a mathematical trick to fit the experimental data, but it soon became clear that it had profound implications for our understanding of the natural world. This idea, which was initially met with skepticism, marked the birth of quantum theory. It was a pivotal moment in the history of science, as it challenged the long-held beliefs of classical physics and opened up new avenues of research and discovery. Albert Einstein further extended the idea of quantized energy. In 1905, he published a paper explaining the photoelectric effect, a phenomenon where light ejects electrons from a metal surface. This was another puzzle that classical physics couldn't solve. Einstein proposed that light is made of particles, later called photons, each carrying a quantum of energy. This explanation not only solved the photoelectric effect, but also provided strong evidence for the quantum nature of light. Einstein's proposal that light is made of particles, or photons, was a groundbreaking idea. It suggested that light, which had long been understood as a wave, also had particle-like properties. This dual nature of light was a key concept in the emerging field of quantum theory. This idea earned Einstein the 1921 Nobel Prize in Physics. His work on the photoelectric effect was a major milestone in the development of quantum theory and further established the quantum view of energy. The quantum view of energy, which began with Planck's hypothesis and was expanded by Einstein, revolutionized our understanding of the physical world. It showed that energy is quantized, fundamentally changing the way scientists thought about the nature of light and matter. Quantum theory evolved rapidly with significant contributions from other brilliant scientists. Niels Bohr, Louis de Broglie, Werner Heisenberg, and Erwin Schrödinger each played crucial roles in developing and refining the theory. Bohr, de Broglie, Heisenberg, and Schrödinger were instrumental in advancing quantum theory. Their work built on the foundations laid by Planck and Einstein, leading to a deeper and more comprehensive understanding of the quantum world. Niels Bohr developed the Bohr model of the atom, which introduced the idea of quantized electron orbits. This model explained the stability of atoms and the emission spectra of hydrogen, providing further evidence for the quantum nature of matter. Louis de Broglie proposed that particles, such as electrons, have wave-like properties. This wave-particle duality was a revolutionary concept that challenged the classical distinction between particles and waves. Werner Heisenberg and Erwin Schrödinger independently developed the mathematical framework of quantum mechanics. Heisenberg's matrix mechanics and Schrödinger's wave mechanics provided powerful tools for understanding and predicting the behavior of quantum systems. Quantum theory revolutionized our understanding of nature, revealing that particles behave probabilistically at microscopic scales. This probabilistic nature of quantum mechanics was a profound departure from the deterministic laws of classical physics. The probabilistic behavior of particles at microscopic scales is one of the most intriguing aspects of quantum theory. It suggests that we can only predict the likelihood of finding a particle in a particular state, rather than its exact position and momentum. Quantum theory underpins modern technologies like semiconductors, lasers, and quantum computers. These technologies have transformed our world, enabling advancements in computing, communication, and many other fields. Quantum theory remains one of the most successful and accurate scientific theories ever developed. Its predictions have been confirmed by countless experiments, and it continues to be a vital area of research, driving innovation and expanding our understanding of the universe.